In this little lecture, we're going to do two things. We're going to review the idea of a truth functional connective and how the tables encode the information about our basic connectives. And then we're going to use tables as a way of answering a very simple question that has to do with truth functions and how they work. So first, the tables. We said that not is truth functional. The idea was whether a negative statement is true depends strictly on whether what's being denied is true. If P is true, someone who denies it says something false. For example, it's true that Pittsburgh is in Pennsylvania. If someone says Pittsburgh's not in Pennsylvania, they've said something false. If P happened to stand for a false sentence, however, for example, if it said that Pasadena is in Pennsylvania, well then, someone who denied that and said Pasadena is not in Pennsylvania would have said something true. The same idea works for the cases where we've joined two sentences with a connective, but it's just that there are a few more steps. So we'll look at the case of or, since that's relevant to our next problem, and then say something quick about the arrow and double arrow cases. First, what's the setup here? We're considering a compound made out of P and Q, whatever specific sentences they may be. Whatever they are, there are four possibilities. Both sentences are true, P is true and Q is false, P is false and Q is true, or P is false and Q is false. Now we look at the table for P or Q and see how it encodes the meaning of or. What we said about inclusive or is that an inclusive or statement is true so long as it has at least one true part. And what we see is in the first three cases, at least one of P and Q is true. So when we go over and look at the column under the or, in the first three cases we have a 1 for true. In the final case, however, if P and Q are both false, then we don't have at least one true part for our or statement, and the or statement is false. So the table is simply recording something that we can say in English in other ways, but when you get a bunch of these things interacting, the table turns out to be a useful tool for thinking about it. Very briefly, just a reminder about the P arrow Q case. As I said, you may not like it, you may not find this table intuitive. In the other little lecture, we explained why someone might go for this table, but what matters at the end of the day is that you remember it, and the easiest way to remember it is to remember the case where it's false. P arrow Q is definitely false when P is true and Q is false. In all other cases, it's true. If you can make yourself remember that, it'll make a lot of other things easier. P double arrow Q is like an equation. That is to say, the double arrow is like an equal sign for truth values. So it's saying that P and Q have the same truth value. In the first row, they do. If P and Q are both true, they have the same truth value. We have a 1 here. In the last row, P and Q are both false. That means they have the same truth value, namely false, and so the statement is true. The two middle rows, the truth values of P and Q are different, and so the truth value is 0 or false. With that in mind, we can now go on to look at a little problem that illustrates the kind of things we can do with these tables. So the idea of distribution comes up early and often in logic courses because the not kind of reminds us of a minus, and in arithmetic we're used to the idea that you can distribute a minus sign over plus. So people tend to think you can distribute a not over an or an and or whatever, and we can see whether that works by using tables in the different cases. So we'll consider this particular case does not distribute over or. In other words, if we deny an or statement, is that the same as taking not the first thing or not the second thing? Is that the same as the distributed version? Now look at the table. This row here tells us when the sentence we're starting with, not P or Q, is true and false. We got to it by reminding ourselves first when P or Q is true, and noticing that when you deny a true statement, you get a false statement. That accounts for the first three rows. But when you deny a false statement, you get a true statement. And so this column here in red tells us in each of the four possible cases whether not P or Q is true. Our question then is when we look at this formula, the distributed version, and we figure out what goes under its main connective, under the OR, will that column of zeros and ones end up matching this? If it does, then not distributes over OR. If it doesn't, then these two things are different. They don't always say the same thing, and the distribution doesn't work. So let's carry on. What I've done here is I've filled in some stuff that will help us get closer to the answer. We've got negative parts on either side of the OR. The truth values for not P will be the opposite of the values for P over here. The truth values for Q, for not Q rather, will be the opposite of the truth values for Q here. So where we had 1, 1, 0, 0 under P, we've got 0, 0, 1, 1 under not P. The 1, 0, 1, 0 for Q turns into a 0, 1, 0, 1 for not Q. And now we're ready to figure out what goes under this main connective and does it match what we have here. Well, for an OR statement to be true, whatever its parts are, what's required is that the OR statement have at least one true part. In this first case, we don't have a true part. Both the not P and the not Q are false. So in the first case, we have a 0 here. And that does match what we find over here. But from then on, things go downhill. In the second case, not Q is true. Our OR statement has one true part, which means it has at least one true part, which means that it's true. But not P or Q is false in that case. So we already know these two things don't say the same thing. Not does not distribute over OR because when you do the distribution, something changes about the meaning. Same thing here. You get a true here where you had a false over here. Now in the last case, well, we've got two true parts on either side of the OR. So the statement is true. Here we denied a false statement, we had a true. So in some cases, the truth value stays the same, but in other cases it changes, and what that means is we don't have an identity here. We don't have an equation. They don't say the same thing. So just a quick recap. We wanted to know, does not bracket P or Q amount to the same thing as not P or not Q? The point was that if they do, when we work out the columns of ones and zeros under their main connectives, under the tilde here and under the OR here, those columns would be the same. What we saw was that they don't come out the same way. The answer was no. You should go on and do the same thing, the same exercise, except confirm for yourself that when we have not bracket P and Q, that doesn't distribute. Likewise, not fails to distribute over the arrow, and not fails to distribute over the double arrow. And those little finger exercises will help you develop your facility at doing truth table problems.